We're going to be talking about this series, The Catalyst of Change, and it's really about how scientific advances are really going to be at the forefront of changes that are going to be really having a huge impact on your life. We have 4 lectures. We're actually, as I said, trying to experiment today, which will be kind of fun. We're actually going to have 2 lectures doing their kind of a lecture off, or I don't know what the right term is, but they're going to be here. Actually, it's collaborative. They're going to be talking about this really interesting idea of what is the future for humans on Earth as well as life in outer space. And so the experiment is, we've never tried this before, of having 2 esteemed people come and talk about science in a collaborative but also sort of entertaining way. So tonight's lecture is called Life Beyond Earth, and I'll just really look at the trajectory of life beyond Earth. So without further ado, let me introduce our 2 speakers. Our first speaker is somebody you've seen before on this stage, Chris Impey. Chris is a University Distinguished Professor of Astronomy in the College of Science. He received his graduate and PhD in astronomy from the University of Edinburgh, and he has been a member of the faculty in the Department of Astronomy since 1986. He works mostly in the fields of extragalactic astronomy and observational cosmology, and has over a... Oh, I didn't realize this was going on. Yes. I guess that's what observational astronomy is all about. Dr. Impey has over 170 refereed publications and 70 published conference proceedings. He's written a number of popular science books. I recommend them to you highly, marked by their incorporation of cutting-edge research and the use of vignettes that place the reader in unfamiliar scenes. Our second speaker is Betul Kachar. Betul is actually, I believe, she just informed me that I believe is our youngest speaker in this series. And remember, we've been doing this for 15 years, so we're excited about having Betul here. She's an assistant professor in the Department of Molecular and Cellular Biology and also in the Department of Astronomy, and that's the connection here you'll see tonight. She received her PhD from the Departments of Chemistry and Biochemistry at Emory Medical School. And this is where I get confused being a physicist. She's studying the structure-function relationship of monoamine oxidases, which I Googled, which has something to do with the control of oxidation of drugs. She'll probably explain that better than I. She was a NASA postdoctoral fellow of the NASA Astrobiology Institute and a research group leader at Harvard University Department of Organismic and Evolutionary Biology before coming to the University of Arizona in 2017. So please give a warm welcome to our 2 speakers tonight.
Welcome, everyone. Am I live? We need a mic? Can you hear me now? Okay. So welcome, everyone, to the warm embrace of science on this cold evening. Betul and I are going to give you 2 different takes on life beyond Earth. And between us, we're going to address a couple of pressing questions. One, will we ever leave this planet? And why and how? And second, what are the prospects of life beyond the Earth? What else is out there as we venture for the first time beyond this planet? The theme of this series is Catalysts of Change, and we're really talking about rapid, almost unpredictable change. And to echo what you're going to hear in a couple of weeks, we live on a planet where for a while, luckily it's starting to tail off, the population was expanding exponentially. And as you'll hear in a couple of weeks, the combination of that exponential growth compounded by our exponentially increasing footprint on the planet in industrialized nations is leading us into some tricky terrain. On the right, you see something familiar to all of us, the exponential growth in computational power, which essentially makes computing free. Data is almost free compared to what it used to be. And this is also a very dramatic change, and you'll hear a lot more about this in the 3rd lecture in this series. Now, there's a hazard associated with the left and opportunity on the right, and it's good to keep in perspective in the middle the fact that the world has grown, and as the power of the world has grown, it's got some good consequences. In the last 50 years, 1.5 billion people have been raised above the poverty level due to a combination of medical technology and agricultural technology. So there's some good stories here, but there's also some hazard up ahead. So we'll keep our eyes on these exponentials. Meanwhile, out in space, astronomers have their own exponential, and it stems from the first discovery of a planet beyond our solar system, just in 1995. And you can see that through the last decade, primarily due to the work of one modest-sized satellite with a mirror about this big, the Kepler satellite from NASA, astronomers have found ever-increasing numbers of extrasolar planets, planets beyond our solar system. And the number is now over 4,000. Again, before 1995, 0 were known. This is a brand new field of science. So this is the exponential growth that seeds astrobiology, the speculation of life beyond Earth, and it underlies a lot of this lecture. And these worlds are not all like our world. This is the topology or the zoology of exoplanets, now that we know there are thousands of them. And yes, many of them are rocky planets like the Earth, but some of them are unrecognizably different. There are worlds that are the size of the Earth, but orbiting a few days, whizzing around their parent stars with surfaces so hot the rock is molten. There are icy worlds far out in their solar systems, or planets the size of Jupiter whizzing around their stars in a week. Remember, in our solar system, the closest planet, Mercury, takes 3 months to go around the sun. So some of these planets are part of unrecognizable architectures of solar systems, and they sort of reset our expectations of what might be out there. But to cut to the chase of the most interesting question for us, these are the frequencies of Earth-like planets based on Kepler data extrapolated through the Milky Way galaxy, because Kepler had enough reach and enough statistics to do this. And you'll notice right away that 1 in 6 stars in our galaxy has an Earth-like planet, but slightly more than that have a super-Earth. Our solar system has 4 terrestrial planets and no super-Earths. So right away, this is a new category of planets that exist in abundance out there, but not in our solar system. If you put these two categories together, you can fairly reliably extrapolate to the number of Earth-like and potentially habitable worlds in just this one galaxy. It's about 10 billion, and a phenomenal number. That is the number of potential biological experiments in this galaxy. And since I'm a cosmologist, I'll remind you that in the universe where our Milky Way is typical, there are several 100 billion galaxies. So if you want to know about the number of potential biology experiments in the universe, multiply 10 billion by 100 or a few hundred billion. It's a pretty amazing number. So what's the next stage in this research? Now that we have very high body counts of exoplanets, it's kind of old hat to find an Earth-like planet. There were graduate students in our department 10 years ago that could get a front-page headline out of an Earth-like planet. Not so much now. They're released in droves, in batches. The next stage of the game is the very difficult experiment of sniffing the atmosphere of one of these Earth-like planets. That is the reflected light of something that's 1 billion times fainter than the star that sits very close to it on the sky, and trying to see in the spectrum of that atmosphere whether you see biomarkers or biosignatures. That is to say, indicators that a metabolism or biology, microbial, exists on that planet. This is an experiment that we're at the epicenter of. Research groups at Steward Observatory and our Giant Magellan Telescope, which we're a partner of for Chile, currently being constructed, will have the capability to make this kind of spectrum for more than a dozen Earth-like planets. This is a very competitive field. Also, in Steward, we have the PI of an instrument on the James Webb Space Telescope, the successor to Hubble, which will also do this kind of science. And this is perhaps one of the most exciting goals in science across fields, not just astronomy, to be able to look for the signature of life in this way. Meanwhile, bringing it back to Earth for a moment, here's another exponential that's a little more uncomfortable. This is the exponential change in the post-industrial era of the greenhouse gases that are changing our planet. And I'm not going to say much more about this, of course, but clearly we're on the cusp of something dramatic that we have to keep in view and do something about. As Greta Thunberg would say, how dare you not pay attention to it? anyone who's not. So you're going to hear more about this in a couple of weeks, obviously. A detailed dive into the biosphere and our impact on it and how we can better understand that to control our own destiny on this planet. Because it may or may not have caught your attention, but just 2 weeks ago, the Bulletin of the Atomic Scientists released their update to the Doomsday Clock. It's a metaphorical indicator of how close we are to annihilating ourselves. And it moved as far as 17 minutes from midnight at the end of the Cold War, a rosier time in history recently. It's moved much closer to midnight, and just 2 weeks ago, it was moved to 100 seconds to midnight, the clearest warning sign we could possibly want. And this is based on the conjunct of our lack of control over the nuclear weapons we have, our lack of control over the climate change that we're causing, compounded and multiplied by cyber warfare and misinformation that we're all familiar with. This puts us in a precarious place. And since my topic is partly, will we leave the Earth, let me just make the obvious point that although I would like that we leave the Earth for reasons of pure exploration and adventure and curiosity, there's also the possibility that we might have to leave the Earth. But I'll just say it right now, there is no plan B, and there's no planet B. The nearest Earth-like planets that you're going to hear about are hundreds or thousands of trillions of miles away, and no more than the tiniest fraction of humanity will ever go to them in the foreseeable future. So we have to take care of our business on Earth. But I'll talk about how we might get out there. So what's the state of space? I would say the state of space and space travel is very robust. State of the Union? Not so sure about that. It's a young activity. Space travel, for most of its history, has been the domain of two superpowers duking it out, a geopolitical pissing contest, if you like. So that's a very strange historical predicate for this activity that could have been noble, could have been about pure exploration, and is still in some part. It's worth remembering that just under 600 people have ever experienced zero gravity in Earth orbit. It's not even that far, to get it in perspective. Earth orbit is about a half an hour's drive straight up, that's all. It's pretty hard to do, but that's not that far. And just a dozen people, all as it happens, white men from the Midwest, strange selection effect there, have stood on another world, the moon. And it's almost half a century since we were there. Most Americans were not alive when that happened. It's the dimmest of cultural memories to them from grainy black and white TV footage. So looking at this, it would be easy to think we're in the doldrums. We're not going anywhere in space. But I think we have to take the long view and remember this is a new human activity. It's young. Also, we shouldn't be too hard on NASA. This is NASA's budget over that time frame. And the budget that NASA had when we went to the moon was a pure anomaly, 10 times higher and unsustainably high. And it ran and collided with the Vietnam War, which meant the last 3 moon missions were canceled. More dispiriting to planetary scientists and astronomers is the decline in NASA's budget in real terms by a factor of 2 in the last 20 years. So it's unrealistic to expect NASA to do bold, visionary, magnificent things when they're locked into the predicate of an election cycle and a diminishing budget. Interestingly, on the other side of the world, things are different. The Chinese space program is very robust. The tick marks show the accelerating rate of their manned and woman launches. They're called taikonauts, the Chinese astronauts. The Chinese are planning a space station, a moon base, and a Mars base. And where their space program, twinned with the military-industrial complex, so it's pretty secretive, has been growing at the rate of their economy for decades, they can do some pretty impressive things. And so we're witnessing a new superpower rivalry in space. But the thing that's interesting, and the thing I want to focus on, is of course what's happening in the private sector. From beginnings that it will be hard to project into the future, less than a dozen space tourists have paid of order $10 million each to go up in the Soyuz launch vehicle and spend some time on the space station. It doesn't really seem representative of some larger activity. More interesting and indicative was the X Prize, a suborbital competition modeled on the Lindbergh Prize, which essentially kicked off civil aviation in the 1930s. And that X Prize really fueled the intense commercial activity that has led to advances in the private space program. And we know many of these players. There's the publicity-seeking Sir Richard Branson and his Virgin Galactic company. And even though there are obstacles, they're riding through the obstacles. The prototype for Spaceship Two crashed a couple of years ago with the death of a co-pilot, the near death of a pilot. Now, Branson's accepted $30 million in deposits from essentially an A-list of celebrities who wanted to go on this zero-gravity joyride for 7 minutes, because that's really all it is. He offered all of them their money back, their deposits back, no questions asked, after that catastrophe with fatality. And almost nobody took the money, or nobody took the refund, because even the average civilian signing up for this, they know it's dangerous. They're willing to take the chance. It's an adventure. Meanwhile, we have people like Jeff Bezos, the founder of Amazon, and his Blue Origin company, a little more secretive. We don't always know their plans. They have a launch vehicle that can take people into orbit, and they're preparing a moon lander. Elon Musk, founder of SpaceX, just several years ago took a huge step in the future of space travel by showing that he can reuse his rockets by landing them on a platform in the Gulf. And that is as hard as it looks. That is rocket science, and that is a game changer, because in the history of rocketry up to that point, the rockets were disposed. It was very expensive. And that was Falcon 9. Musk has rockets planned that will eclipse even the mighty Saturn V and take astronauts, we hope, he hopes, to the moon and Mars. In SpaceX documentation, his SpaceX Starship is called the BFR, and I'll leave you to guess what the acronym means. It's dangerous. People will die. Spaceship Two, people already have died. But again, the risk is understood, and this is what happens. The graph shows a decline of 2 orders of magnitude in the fatality rate in civil aviation in its first 50 years, just due to innovation and safety technological breakthroughs. And the same thing will happen in the private space program. So even if it seems somewhat dangerous now, it's going to get safer. And even if it seems incredibly expensive now, it's going to get cheaper. This is reliable. There are hazards associated with going into space, and not all of them are easy to anticipate. The other hazards are associated with the toilet thing in zero gravity. I'm not even going to go there. The economics are actually fairly robust, even at the beginning of this adventure. Here's the growth rate in the number and the net worth of billionaires, and many of these billionaires are the players in this game, and they've put real skin into the game, their own personal fortunes on the line, a good fraction of $1 billion from both Branson and Musk. And so they are driving the activity, but they're clearly projecting to an activity that could affect a large number of people. And I got a sense of this when I compiled data to show the average cost of a movie and the average cost of a NASA space mission. So this is not private space, this is NASA. And interestingly, about 5 or 6 years ago, those curves crossed. So the average movie does now cost more than the average space mission. And if you want to make the analogy very direct, if you just happen to have $400 million burning a hole in your pocket, you could make a really cool movie with a famous director about life on an exomoon, or you could build this Kepler spacecraft and find hundreds of Earth-like planets for real. They cost the same. So is your next vacation going to be somewhere in the solar system? Well, maybe not your next vacation, maybe your next but 2 or 3 or 4, but I think it's going to happen. The solar system will be our oyster within a few decades, I truly believe. And if I were analogizing it to something that is familiar to everyone, and it's strikingly similar, the paths, the timelines were a little different, I would take the internet. The internet had a pioneering phase And the visionary behind this is almost unrecognizable. J.R. Licklider wrote a white paper for the RAND Corporation in 1960, which at a time when computers would have filled this stage and up 2 stories, he envisaged the wireless internet, data in the cloud, handheld devices like we have now. He did that in 1960. It was incubated by the military-industrial complex, and so the first people with email in the 1970s were people in research institutes and military installations. Civilians didn't have it. It became a research tool. The CERN was the incubator of the web browser, of course. And 1995, this time, in this evolution, we can pinpoint an actual year. It was so dramatic. In 1995, 2 graduate students at Stanford figured out search. A strange company called Amazon was formed. Nobody really knew what that was about. Why would you want to sell books online? And the first internet service providers came into being. And I would challenge anyone who can remember 1995 to have sat there then and predicted what it would be like now. That's how fast it's been. That's the exponential change. So, hopefully not forcing the analogy, we see a very similar progression in space travel. We have the pioneering phase. And who could have imagined when Robert Goddard sent his small liquid oxygen rocket over 186 yards of his Aunt Effie's frozen cabbage patch in the Midwest, that you would have the mighty Saturn V within a few decades taking astronauts to the moon? That's the visionary. Then incubation by the military-industrial complex, a little awkwardly in this case, because Wernher von Braun, when he was secreted away to become part of the US space program, to my mind had the blood of about 15,000 Europeans on his hands from work in the slave factories and the V-2 bombs that fell on my hometown in Britain. But that's how it goes. The sausages get made. We went to the moon. Goes into the research arena with the space shuttle, which had a mix almost equal of military and civilian payloads. And now I'm going to speculate, I won't put it as pinpoint as 1995 for the internet, that perhaps around now we are seeing the takeoff to the final and 4th era, when looking back in 20 years from now, it may be unrecognizably different because of the rate of change. And so here's the numbers of that. Here's the history of launches through the Cold War, through the heart of the space program by governments, mostly the US and the Soviet Union, more recently China. And here's the new aspect, the commercial launches. And what's notable is that 2017 was the first year in the entire history of the space program, over 60 years, where there were more commercial launches than launches by governments, a clear harbinger of things to come. And this is the curve. This is an exponential too, but it's been squashed with a logarithmic scale. And this is the cost per kilo of launch into orbit, and you can see that just in the last decade, that price has been depressed, pushed down by a factor of 10. And we're heading to a place where it will become cheap. So in maybe just 10 years from now, the cost will be such that, and so I'll ask it as a question. I can see your hands if you put them up. So I'm going to ask all of you, if going into Earth orbit and having a few days at the space station or at a space hotel, they already exist, cost about the same as a high-end holiday and was as safe as driving a car, how many people would do it? Okay. And I think it will be. Notice that I said as safe as driving a car, because we know that driving a car is about 20 times more dangerous than flying. I think space travel will be safer than flying, and maybe a little more dangerous than driving a car. And at the point where we get a space elevator, which is the Indian rope trick of a cable flung into space such that the centrifugal force of the Earth is balanced by the weight of the cable, and you have enough tensile strength in the material that it doesn't break, it's free. You don't need rockets, you don't need fuel. You just use solar-powered elevators to go up and down into Earth orbit, and then you can go anywhere. And that is within sight, maybe a few decades from now. Well, I'm extrapolating a few decades, but I want to, again, draw back and take the big picture here, because this is a long activity. Humans have been around for a while. So I want to ask you to think about the analogy. It's only a few tens of thousands of years from the tool that let us hunt and sustain our population on the primal Earth. It's only a few tens of thousands of years from that to the iPhone. And I want you to imagine what 10,000 or 30,000 years more from the iPhone is. What will that even look like? How would we even understand that? How could we predict that? The future is deliciously hard to predict. And moving more into Batul's arena of biology, the Earth has been alive for 4 billion years. Most of that time, microscopic, invisible to the naked eye. And so, in the few billion years that it took to go from microbes to us, we must acknowledge that there are Earths out there that have had a head start on this Earth, warmed by their sun-like star, that's 3, 4, 5 billion years more than our history. So what would it be like to play forward evolution from our state for another few billion years? Very hard to imagine. But we should imagine it, because out there in the universe, it's undoubtedly happened. This echoes the topic of the third lecture, the exponential rate of change in computation. But I'm aligning it with another thing, which is the capability of that computation to exist in a sensing package that can understand its environment, a robot, essentially, a robotic organism. And you can see the incredible trajectory of a century of computing on a logarithmic scale. And you look across and you see that the best robot aligned with a computer is something like a guppy or a lizard, and that's about right. The best autonomous robot is not that impressive. It's like a lower order reptile or mammal. But if you project, then we're only a few decades away from humanoid intelligence in a robotic package, artificial intelligence. And I think what's more striking, since we're here to talk about biology as well, is that progression in 100 years has done what biology on the Earth took 3 billion years to do. That's the acceleration of technology. It's just phenomenal. And there are projects out there to try and get us to the stars. The Breakthrough Starshot project will use powerful lasers. These are all technologies that exist. Banks of powerful lasers, tiny spacecraft attached to solar sails, maybe a meter across, made of gossamer-thin material like mylar, only even lighter. And that radiation will propel them and accelerate them to a few percent of the speed of light, maybe 5% of the speed of light. And in this instance, go to the nearest star system, where there's a good shot of Earth-like planets. And so this is an actual project under development to send, in 2 generations, remote sensing probes to see what there is on, hopefully, Earth-like planets around the nearest star. Very exciting. And why should we imagine we were the first to do this? If anyone has done this, then traveling at 5% of the speed of light, it's a short blink of an eye in the age of the galaxy to spread across the galaxy. So it's not a question of whether we go physically, but if we send our robotic emissaries, which is just remote sensing, extensions of our senses, out into the galaxy, we're on the cusp of doing that, leading to invert the question and ask, well, has anyone else done it? Are we the only ones to do it? And so maybe there is a far future vacation where you're actually going to the stars. So to finish my part, I want to talk about going to the stars. It seems premature. We haven't been to the moon for 50 years, and I'm talking about going to the stars. Is that even possible? Well, not with what we have now. All that Elon Musk and Jeff Bezos have done is they've refined the existing chemical rocket. It's still vastly inefficient. Nuclear power, envisaged as a pulsed system, or maybe one better still, which doesn't carry its fuel, but uses a big scoop to catch hydrogen in the interstellar medium and fuse that, these are millions of times more efficient than any chemical rocket. So that's the advance that's sitting there with existing technology that we've not used yet. This, maybe not. This sort of breaks the laws of physics. And trust me, the laws of physics are a bitch. You can't mess with them. So I don't think the Star Trek thing is going to happen. But what might happen is we might take ourselves down into a wait state using technology in medicine that is actually maturing quite quickly for suspended animation. And I actually think it's less likely to be in the sense of humans taken into a cryo state in pods as on the left, And this is a little creepy, I understand, but you'll just stay with me on this. The most efficient way to do it is to have embryo starships. So you have cryo-frozen embryos, and that, again, can be done on the Earth, so we know this technology exists. And then in a much more efficient package, you can send this to the next star system. Now, this would be curated by robot nannies who would have to bring these embryos through to their development phase when they get to their destination and onto their home planet. And since I know that I'm creeping you out, I'll say that Batul has a much better way of envisaging this, which is instead of sending people in pods or embryos, we just send the ingredients for life and then see what happens. And that's a good way to go. So we have this system, this fabulous system, which I will use as the icon of exoplanets. It's the TRAPPIST-1 system, and it has 7 terrestrial planets, 3 of which are Earth-like in their habitable zones. And to set up the transition from near Earth, me, to Batul, imagining her on TRAPPIST-1, let me give you a little scale model. So if I'm sitting here illuminated by the sun, that spotlight overhead, on that scale, the furthest that most humans have been, the 600 in Earth orbit, is literally hair's width. It's tiny, tiny scale. That trip to the moon that a dozen people did, it's this. The solar system is on the scale you're sitting in. Jupiter would be about halfway back through Centennial Hall. The solar system would fit pretty much within the U of A campus. And if I imagine my compatriot Batul is at TRAPPIST-1, illuminated by her not quite sun-like star, it's actually a dwarf star, then that distance to that fabulous system where we might find Earths and biology is 20,000 miles away. That's how far we have to go before we sleep. And so let me hand over to Batul for the second part of the talk.
Thank you. Thank you. Thank you very much. Chris outlined the technological developments that are available to us to explore what is out there. And if we exploit this carefully, we might be transforming to a true space civilization for the first time for our entire human history. And I want to ask this simple question. Why do we do this? And you might too. Why do we bother? What is waiting for us out there? Why do we want to explore space? And that is the question that I would like to explore with you today, and I will give you 3 very quick reasons why. Reason number 1, exploring space may allow us to acquire space-based resources. And any resource that we can obtain directly from space is a resource that we can keep untouched and protected here on our own planet. Reason number 2, settling, surviving, and visiting other worlds may allow us to improve our problem-solving skills. We may cooperate with one another better, we may communicate with each other better, and we can solve problems better as humans. And reason number 3 is the reason why we are here today, and that's exactly what I want to talk about. Exploring space and life in other spaces, in other places, may actually allow us to understand the likelihood of life's existence elsewhere in the universe at the larger scale. And that's really at the crux of what I'm interested in. There are 2 questions that are on the slide right now, and I think they're intertwined. Are we alone? And how did life on Earth begin? So a quick show of hands before I drill down. How many of you here think that we are alone in the universe? Show of hands. Wow. Okay, how many of you think that we are not alone in the universe? Get this. So what is interesting about this question is I think regardless of the answer that you give, it is astounding. So none of you thinks that we are alone in the universe as far as I could see, but imagine that we were. Okay, if this is indeed the only life in the universe, and if we are alone in the universe, then this makes biology the most unique science in the entire universe. This is the only place to study biology. That's mind-blowing, if we are alone. You can study physics, You can study geology, you can go and study rocks, you can study chemistry pretty much anywhere, but this is the only place to study biology. And if we are not alone in the universe, then we are assuming that life and biology is pervasive across the entire universe. Pervasive. That means that life can occur more than once and maybe frequently. But then let me ask you, if that's in fact the case, and seems like almost all of you believe that that is, why don't we see life originating frequently right here on this planet, if it is so easy for it to happen? Why do we think that life originated once and billions of years ago, and that is it? And scientifically, why can't we create life in the lab? Why can't we make it? Where is it? Let's start by exploring whether we are alone in the universe. This is a question that we've been asking since we gained consciousness. We developed technologies such as the Kepler Space Telescope to finally explore what is outside of our doorstep, what is outside of our solar system. We've been exploring planets. We found that there are thousands of planets out there, and we didn't even survey the entire sky. We directed the telescope towards a small fragment in the entire sky. Imagine that this is the entire sky. We literally looked at only maybe a space that will be covered with a single hand of yours, or maybe two. And despite that small area that we peeked through, we found that there are thousands of planets out there. Some resemble our own planet Earth in terms of size, in terms of temperature, and some resemble other planets in our solar system in terms of size and other properties. This is very exciting. And I will take you to a particular one that Chris also just took you to. It's the TRAPPIST-1 system. And the reason why I want to take you there, now we're traveling about 40 light years away from our own system. We are greeted by a red dwarf star that's much smaller than our own sun, and orbiting this are 7 terrestrial planets, 3 of which are planet Earth size. It's marvelous. If you stand in one of them, you can see the atmosphere of the other on a clear day, I suppose. But is that a good reason to visit this system? We have technological abilities, but we don't have limitless resources. We need to find the perfect system so that when we invest on it and when we visit it, we have reason to believe that something is waiting us for there to explore and understand in terms of life's existence. So where do we go? We don't want to just survey the sky, right? And I will argue today that it is unlikely that we will find whatever it is that we are looking for, and specifically light itself in this case, without understanding how life originated on our own planet. We need to understand the conditions that gave birth to life here if we think that the universe is pregnant with life as we speak. How did life on Earth begin? Sadly, I won't be giving you the answer, not yet, but you hired me, so I'm working on it. So it's been only 2 years. Well, let's go to Star Trek. Q explaining Captain Picard. How did it all begin?
You see this? This is you. I'm serious. Right here. Life is about to form on this planet for the very first time. A group of amino acids are about to combine to form the first protein. The building blocks of what you call life. Strange, isn't it? Everything you know, your entire civilization, it all begins right here in this little pond of goo.
He's not buying it. But he should, actually. The reason I show you this is because this is one of the most accurate descriptions of life's origin as far as it goes. There are no continents back there, and they think this is happening in France. I wanted to correct that. But I think in the entire science fiction media out there, this is one of the most accurate descriptions of life's beginnings. We are imagining inhabitable planets, volcanoes, really hot temperature, and a goo in which life originated. And we've been asking these questions way before we started making movies. Going back to ancient Greece, Aristotle, I think he explored life's origins, I think, in more than one way, but what I want to highlight today is the concept of wider principle, a thing that embodies the natural body, the whole potential of life. So we go way back. We've been asking these questions philosophically, theologically. And then comes Darwin. Not only he asks the question of life itself, of what life is, he develops ways for us to understand and study the complexity of life and how complexity of life changes over time. And he, in fact, writes about life's origin only once, where he talks about a warm pond, a goo, that life may have originated in. And that's the only line I could find of all the readings that I made from Darwin, where he talks about the origins of life. I guess one revolutionary idea at a time. And then comes, we are traveling way back in the future now. We have studies that are done by Franklin and her colleagues, studying the molecules such as DNA of life. So now we are moving forward from describing what we see around us to drilling down and taking pictures of what makes life possible at the molecular level. We now understand DNA. We know that it's inherited. It is shared across all terrestrial life, that as we know. And since then, we've been exploring what is inside the cell in so many different ways. We can study the molecules, the micromolecules, the proteins, the enzymes, the DNA, RNA, and how they move in time. We can take their pictures. We can record them in action. But relevant for origin of life studies, we did not stop just by looking at what is inside the cell. We moved forward and asked, can we create the molecules that make up life without life itself? Can we create the molecules that make up biology without biology? And this is what Stanley Murray and Urey asked in their infamous experiment, where they simulated and generated an early Earth condition in terms of lightning and hot temperature, and generated amino acids in a flask. A variety of different amino acids that we still study today. So great. Not only we can understand life, describe it, and study its properties, we can also drill down and study life at the subcellular level, but we don't only stop there. We also make these subcellular components in the lab without life itself. But does that make life? Does generating amino acid make life? Do generating RNA, DNA molecules make life? No, it doesn't. The question still remains, how can groups of molecules exhibit life-like behaviors? We want to move forward from making amino acids in the lab. We can do it all day. That's not life. Do you see a fish crawling out of a flask? No, sorry. So let's travel back to the origins. And I'm taking you all the way back, right? We're going all the way back to the formation of Earth. That's about 4.5 billions of years into the past, okay? We have a stable atmosphere fairly rapidly. Within the first 100 million years, we see that happening. And then we have the Hadean Earth, that is from Greek, hellish, as you saw, where Captain Picard visited. That was not very habitable. That's really what we think Hadean Earth looked like, how we think it looked like. And this is a planet, our own planet, that is packed with abiotic chemicals. Abiotic chemicals are still around us, but we also have life. I mean, look around you. But back then, it was only abiotic chemicals. And this is exactly when a miracle occurs. Around 3.8 billions of years ago, we have the occurrence of the first cell. So somewhere between 4.2 billions of years to 3.8, life emerges. This is where the miracle happens. And that's what we want to understand. How did a pool of abiotic chemicals transition into a life-like behavior, or behavior-exhibiting group of chemicals? And then how did life emerge from this? And this is what life does. We've been studying this for a long time. And this is not even the whole picture. And this is a big screen. And I did my best to fit as much information as I can. This is the highest, this is what they allowed me, this is it. And you're looking at inside of you. This is happening in human systems. A small segment of human metabolism. All these arrows are representing the pathways, ins and outs, a lot of chemistry going on here. This is happening inside of you. So we can study life, no problem there. And we went a little step further from that, from studying life to defining it. What is it that we are trying to find? So over a little decade ago, a group of NASA scientists, they get together and they wanted to understand whether they can even define what life is. And I'm imagining a week-long, the minimum debate about this, and they came up with a final definition. Life is a self-sustaining chemical system capable of undergoing Darwinian evolution. And what is really inspiring me in this quote is that I can see Aristotle in there. That's the question, right? I can see Darwin in there, natural selection, Darwinian evolution. I see Rosalind Franklin in there. We're looking for inheritance, self-sustainability. I see Miller and Urey in there. So all these centuries of questions that we've been asking finally led us to defining life in one sentence. And we know a bit more than that about life. Right? Not just what life is at the cellular level, but what life is at the broader level. Life exhibits itself at the hierarchical level. We're going from molecules, that you can imagine this at the bottom. There's an undeniable increase of complexity as we go up, from molecules to cell groups that then form organisms, populations, communities, ecosystems, and then finally biosphere. And each of these layers, we are not talking about a building with different flats. We're talking a dynamic structure. Each of these layers are communicating with one another. There are relationships that connect each of these layers. There are self-similar patterns of interaction. And each level is somewhere between a machine-like rigid structure. Life is not like a machine. It's not rigid. But between a rigid structure to a more flexible, a chaotic, very chaotic system. We don't want that either. And there are rules between levels as well, the way they interact with one another. And what's fascinating as someone like me who studies life at the molecular level is that what happens at the molecular level, at the bottom, can have a direct impact at the whole ecosystem of the whole biosphere. That's magnificent. So, let's go back to our motivation. Are we alone in the universe, right? That's what we want to know. So, looking at this, first of all, how many of you think there's life here? Okay. Well, we want to understand whether there's life here. So let's together join me, and let's create. We have all the resources for a minute. Let's imagine that. And we built a machine, and we sent this machine to another planet. And this is what the image, and let's make sure the machine or a robot has lens. All right? So this is the picture that the machine sent us. And all together, right now, we will explore whether there's life here or not. All right? So the machine sends this image. It transmits this to us. What do we do? What's that? Drill down. Okay. So let's make this machine more sophisticated. Let's drill down. Well, I'm showing you a lot of rocky structures. So there's a lot of geochemistry going on here. But guess what? Spoiler alert, there is life here. There's life on these rocks that are feeding off of these rocks. There is life inside these springs that I'm showing you. But we can't see it through this picture. So let's imagine that this is the image that this machine sends us, because we just did what you said, we drilled, and the lens recorded whatever is going on and transmitted this movie to us. Would you be convinced that this is life? How many of you think this is life? All right, yeah. Spoiler alert, another one, it is not. It's lifelike. It's funny, isn't it, when you feel like this gut feeling, I feel like there's life in there. Well, congratulations, you're an astrobiologist. But it isn't true. In fact, you're looking at a group of liposomes that are interacting with one another, that are creating spherical, circular structures, that are then organizing into larger groups, and so on and so forth. Interesting. Now think about why you thought this is life. It's moving. There is some structure, right? And think about what I just showed you, hierarchy. There is some hierarchy here. Small molecules got together, formed larger groups, and then larger groups were formed, but they were still connected with one another. There is self-similarity in each layer. So we created a little ecosystem, but guess what? It's not life. It's not capable of evolving. These are what we call protocells. These are blank cells made out of entirely lipids. generated by Harvard, Jack Szostak's laboratory, who's a Nobel laureate who studies origins of life right now, who is working on making these cells encapsulate certain molecules that are capable of evolving. But this is not life. However, there's a lifelike behavior in there, and this is exactly the problem. As I said, we can generate these building blocks, we can make amino acids in the lab, we can make DNA, we can synthesize proteins even, peptides, we can do it. But how do we go from a mixture of chemicals to a rather simplified version that I'm showing you here, a lifelike behavior? How do we do this? And interestingly, based on my reading, it seems like, at least in the literature, once we generated these amino acids in the lab, like through Miller-Urey experiments, people thought that this will be rather straightforward. How difficult will it be from going a mixture of chemicals to a chemicals that form some sort of a network that then behaves like a biological network? How hard can this be? Turns out harder than we thought. Makes it interesting, right? The question, if we drill down then, can a chemical system even exhibit a lifelike behavior? What am I even talking about when I say a chemical system behaving like life? Right? And do the chemical systems that led up to living systems show similar organizational attributes? So let's look into this. I will show you first a rather detailed version of what I've previously shown you about the hierarchy of life. We are looking at simpler, the least complex forms, energy inputs, through subcellular micromolecules to cells, and then we go all the way to the biospheric level. In this case, I'm showing you populations and biogeochemical cycles. Each of these arrows represent some sort of interaction or rules that are taking place in each layer, and also how that layer is connected to the layer below it. And what is interesting is that the layer beneath the top layer is required for the top layer to be present. They build on one another. We did a survey of literature, and we did some experiments in collaboration with Tokyo Institute of Technology since I started here. And we came up with multiple reactions as outputs of our own experiments, and then we surveyed all the other chemical reactions that we could find as sensible in the literature. And what we are finding, and this is the recent article that we just submitted for peer review, is that chemical systems can in fact look like a biological system in terms of the hierarchical organization. Similar to life itself on the right, we're looking at energy inputs, primary radicals, and getting more and more complex as we move all the way to the top. From a simple radical chemical to a more complex chemical structure that are still able to interact with one another. But think about what NASA says, and I work for them. Needs to evolve. Does this evolve? No. But again, I think I have some time to make this happen. So what we are looking for is a chemical system that is able to evolve, not only respond to the environment, reproduce, sustain itself, get more complex in time, and do all of these abilities that life itself does. So, why do we want to do this? What is in it for humanity, aside from solving the biggest problem that we have? How did life begin? So for that, I want to give you a small example of how can we use this information. And this is, again, a very recent article that came out only, I think, last month, that shows how we can use origin of life chemistry for real-life applications. So now think about, let's say, computers. Our life depends on them more than I think we want our lives to, but they do. And think about how much energy it is required for a computer to run the most simple thing. Imagine opening your laptop, putting it on your laps, and checking your email. Okay, maybe you did a little bit more than that. You went on Facebook, and it's been 2 hours now. And you know what? Your laps are burning. The computer is hot. It can't handle even the simple email checking and a little bit internet surfing. There's a lot of energy consumption by this electronic that you're using right now, the computing system. Okay? So we want to know whether we can extract information from biology to use as an alternative computation source. What I mean is that No chemical system, no computer that we have right now on Earth can do what a biological system can in terms of computation. We are, as living organisms, are far more advanced than any computer that we ever built. I will give you a simple example. Think about yourselves as individuals. It's about 8 p.m. Think about what you have done over the last 2 hours. You got in your cars, you drove here, you tried not to get into an accident. Good for you. You climbed the stairs, you walked, you processed the information around you in terms of the weather. Oh, it's going to be cold tonight. And you came here, you listened to the music, you looked at all the room, and you listened to Chris talk, and you're listening to me talk. You're processing the information that I'm providing you. Every word that I'm saying, you're computing it in your mind, trying to understand it. You're computing as I speak. And you're just one person. Now think about this whole entire room and what are we capable of computing in just during the past hour or two. Now think about this whole campus, this town. Think about this country. Think about our entire population as humans, how powerful that is. Biology is a better computer than the computer. And exploring the origin of life chemistry and the lifelike behavior in a chemical system is in some ways exploring the potential and the power of life in a chemical system. And what I mean by that is the ability of life to compute, ability of life to process information, ability of life to innovate, ability of life to tinker. We are looking for those properties in chemical systems. And engineers out there, like this study, are studying origin of life and figuring out the chemistry that enables or potentially may enable life, and using that to build computers that are made entirely out of chemicals. No electronics, nothing, it's chemistry. This is a very simple example. This is the first example, and I'm telling you, you will be seeing more of this. So the theme is the catalyst for change. You're looking at it. This is it, right? So we are able to use chemistry as computers. This is a very simple example. We're processing what's out there. It's a very simple environment that they generated, but it worked. And how can we then use this information for biology? And I will show you a very brief video talking about the possibilities.
The bee is an incredible biological machine. This creature's tiny neuron computer makes trillions of calculations as it maneuvers its body with speed and precision. The bee colony is a self-maintaining, self-replicating system programmed to endlessly continue its task of survival. Through our understanding of the DNA code, we are gaining the ability to create new living machines to our design specifications. The natural world is filled with building blocks of the DNA software, which combined with engineering will open breathtaking possibilities. Fully unlocking this code will bring us the greatest technological advancement ever known to our civilization. Imagine modifying the DNA code of plants to grow living buildings. We can revolutionize construction, architecture, and gardening, creating entire cities out of living organic material. The most powerful computing system known to us is the brain. Once we become capable of programming and organizing neurons, we can create new supercomputers, dwarfing our current systems in power and efficiency. This paradigm in technology and evolution can expand life's ability to colonize and populate our solar system and beyond, sending living spaceships and organisms modified and engineered to live in different extraterrestrial environments. This new self-aware and self-guiding evolutionary process can take life to the next level of existence.
It's exciting, isn't it? Another way of studying the beginnings of life and making sense of the chemical mixture that is available to us, or that was available to us once. My laboratory builds molecular time clocks, as we like to call them, and utilizes modern biology to extrapolate our way back to the beginnings. We want to resurrect, so to speak, the first molecules and understand their behavior in the lab. And we want to evolve these molecules, and we do, to study the repeatability that is involved in life's evolution for the specific molecules that we generate. And one of this molecules that we've been studying is Rubisco. The reason why I wanted to highlight this one very briefly is because we, as humans, and majority of the organisms, we consume carbon. We need carbon to be generated. We need biomass to be generated for us. But we want to know as synthetic biologists, and that's a part of the work we do as well, why? Why is carbon fixed a certain way that we see it today? Are there any alternatives? So instead of trying to engineer what is available to us today, we go back to the origins of these molecules using a variety of different methods, and then try to resurrect their versions that they were once, billions of years ago. We want to access to their own origin, so to speak, and explore their own chemical space to see if there are other possibilities. And the goal here isn't necessarily to look for Rubiscos out there. I, in fact, do not expect Rubisco to be waiting for me to find it on another exoplanet. Would be cool, but I don't think so. However, we want to understand how a certain chemical mixture would give rise to certain micromolecules that profoundly impacted our own atmosphere and life on this own planet, on our own planet. So we use origins of life chemistry and what happened billions of years ago as a source to understand the possibilities. And I want to end up with an idea that I've been wanting to talk about. And I'm writing a mini paper about this, but I wanted to share with you. I'm in good company. So the thing that I've been thinking as a thought experiment is that what if we, instead of sending life somewhere else, and you may be familiar with the concept of panspermia, that suggests that life may have even been transferred to our own planet. Instead of sending life elsewhere and planting these seeds elsewhere, why don't we send chemicals that may evolve into life in response to the very specific condition of whatever the planet that we are sending these chemicals to? We will most likely find a lot of planets that have no life. That's also a very difficult question, right? We are not only looking for life's existence, but we are also looking for life's absence. We want to be sure when we say send that machine elsewhere, tell me, yes or no, do you see life or not? We are a bit bossy, I guess. We want to know. So when the answer comes to us, what is it that we're looking for? We want to quantify life. And this may be one way, right? Sending chemicals through, and I will assume perhaps Amazon will start delivering packages to exoplanets at some point, through a delivery box to a planet of our choice, and then let that planet do its thing and co-evolve with whatever the chemical pools that we are sending that will flourish life that is specific to that planet. So we are not contaminating other planets with our own life. We are just sending chemicals. With that, I would like to say thank you. Thank you for this opportunity, and thank you for coming tonight.